Surya HANA Academy. We're going to start the session in 1 to 2 minutes. Sorry for the delay. Okay, so we'll start the session now. So first I'm going to recap for last 3 weeks what we have covered, and then just give me 10 minutes to recap the entire sessions until now, what sessions we have covered. From there we will start visualize plan, the internal working of the views, how views work internally, and to see the path of the query. Just everyone, anyone can ping me if they can hear my voice clearly. Any of you can ping me. Okay, thank you. Okay, so when we first started the session, we started with what are in-memory databases, what is a column-oriented DB, parallel processing, and then we tried to see how to log into the system, and then quickly we started with business scenario, and based on the business scenario, we wanted to create an attribute view. We learned that attribute views are reusable dimensions used to join master data tables. And then attribute views are of 3 types: standard, time, derived. Steps to create an attribute view: add tables to data foundation, define relationships, define join types, text join, inner join, referential join, left outer join, right outer join. These are the different types of joins inside an attribute view. At least one key attribute we have to maintain, save and activate. Whenever you activate a column view generated in sysbic, column views are runtime views. Attribute views execute on a join engine optimized for processing complex joins. Attribute views are also reusable dimensions. You can reuse attribute views in multiple analytic views. Whenever we execute an attribute view, tables are in catalog. Based on the conditions or the joins or the relationships available in content under packages. A package is nothing but to group together related objects. Package is associated with delivery units to transport packages from one system to a different system. So information views are grouped under packages. Then we see what is difference between derived attribute view and a template. Template you can copy, you can change. Derived is a reference attribute view. Time-based attribute views are used for analyzing time data on hierarchical fashion or different time dimensions. So when you join with a date, you'd like to analyze data based on year, quarter, month. And then quickly we moved on to analytic view. Analytic views are multi-dimensional views. Attribute views are used inside analytic view. They provide master data. Analytic views have data foundation, start join data foundation. A data foundation is a place to define a relationship between tables. You can define a star join, you can define a star schema. In a data foundation, we can define a star schema in the star join data foundation. Both of them execute on OLAP. What is OLAP? OLAP, online analytical processing. OLAP is optimized for mass aggregation of data, parallel processing of a query. When you design a star schema in a data foundation, you define a relationship between tables where you cannot reuse master data. When you define a star schema in star join data foundation, in a star join data foundation, attribute views are used as reusable dimensions. So the limitation of an analytic view having only one fact table, you can request measures only from a single fact table. If you want to request from multiple fact tables, then we need to denormalize using ETL. When you move data from source to target, we can denormalize in the process of moving data and finally get into one single large fact table. And based on that fact table, we can create analytic views. When we create analytic views, we have calculated columns, restricted columns. Calculated columns are used to derive new column based on existing columns, like measures. So you can take two measures and derive a new measure based on existing measure. Restricted columns. Restricted columns are used to filter attribute values on an attribute on a measure. So restricted columns, you can use a measure and an attribute. When you create a restricted column, you have to based on an attribute and a measure. For example, like I would like to see data only for a particular year. For 2015, what is my gross revenue? Employees per absent in office. You're trying to restrict headcount on employee. You're trying to restrict headcount on employee present, absent, or working overtime. So this is a restricted column. The difference between a calculated column and a restricted column: calculated column is between two measures, restricted column is between an attribute and a measure. Now, once we completed this, once we activate an analytic view, it creates a multi-dimensional view. When you use attribute views inside an analytic view, attribute views still don't execute on join engine, rather they execute on overlap engine. When attribute views are the part of the analytic view, they still execute on overlap engine. When we execute attribute views individually, they execute on join engine. And then we quickly seen a scenario about COPA. In COPA, why we have to implement COPA for HANA? Because of the performance, row versus column. In ECC, it stores in row. In HANA, it stores in column. It stores in disk. Here it stores in memory. ABAP does sequential processing. SQL script does parallel processing. Performance. When you generate a report in COPA, it's very time consuming. Like we see KE24. The same report when we design in HANA, it's very, very performance optimized. We can ask any kind of question. We can get answers, broader question, deeper question in a very simplified way. And we can take good decisions at the rate of speed at which HANA delivers data to the business. And then we started to create a scenario wherein we want to create a calculation view. So I created two analytic views, one for actual, which gives me actual profitability analysis data, and the other one is plan. I created a plan analytic view, which can give me plan profitability analysis data. Now I want to design a view in where I can combine both actual and plan in HANA. So in order to combine two fact tables and to produce measures from two different fact tables, I require a calculation view. What is calculation view? Calculation views, you can use data sources, views and tables. You can use different operators like join. Join is a query based on a condition. Union to combine. Projection, selection. You can do filters. You can do calculations inside projection. Aggregation, how we would like to summarize a measure. We have union, join. Aggregation, you have rank. Rank is nothing but you want to calculate top 10 customers, top 10 materials. So union, combine, join, query based on a condition, aggregation, how you would like to summarize measures, rank, and projection. Calculation views have three data categories. One is the dimension, the second one is cube, third one is cube with star join. Dimensions are used for master data. Like dimensions, for dimension modeling, we have two. One is attribute views, the second one is a calculation view. Attribute views are used inside analytic views. Calculation views of type dimensions are used inside calculation views of type star join. Why? Why we use calculation views of type dimension star join? The reason is star joins are executed on SQL engine. Excuse me. Star joins execute on SQL engine. Attribute views execute on join engine. When attribute views execute on join engine, which are optimized for processing complex joins, the same attribute views cannot include in an SQL engine. That's why SAP has a limitation not to use attribute use inside calculation view, but still we would provide master data. So we created a calculation views of type dimension to provide master data for calculation views of type start join. So inside a start join, we've taken both actual and plan. We tried to combine using a union. So after union, we produce a result, measures requesting from both actual and plan. The difference between a calculation view start join, it executes on C engine. The same calculation view of type start join execute on SQL. The difference is C engine is optimized to process complex calculations, whereas SQL engine is optimized to better join determination technique. So this is more optimized for when you design data models like normalized tables, when you have ECC powered by HANA or Business Suite powered by HANA, when you kind of design operational data models, not the data models on the analytical side. We see in the analytics, the difference in analytics and operations. In operations, tables are kept small to write data faster, normalized tables. In analytics, tables are very large, like fact tables having redundant data, having billions of millions and billions of records. Because OLAP has fast scan of data, it can scan data very effectively. It can aggregate data very effectively. So what the OLTP is not good. The transaction processing engine. Let us take ECC powered by HANA. In ECC, it is optimized to write data into tables. The engine that ECC has is OLTP engine, not OLAP. When ECC is powered by HANA, HANA has an OLAP engine. A database has OLAP engine. The application, above application layer has OLTP engine. So when you fire a query in HANA, we are not firing on the ABAP layer, but we are firing in the native HANA. So for the first advantage of designing data models ECC on HANA, we can exploit the potential of OLAP or SQL engine. You can design OLAP or you can design to go for an SQL engine because the tables are designed for normalization to insert or write data faster. Now the same tables we would want to read faster. To read faster, we need to have engine, very powerful engine that can produce or that can crunch data very effectively. That is done by the SQL engine. That's why the star joins, when they execute on SQL engine, are very efficient. Then they execute on C engine, which is optimized for calculations. So and hence, later we decided SQL engine is faster when we executed a report on the calculation views of type star joins. So that is where we completed until the last session. Then we wanted to go to a different topic altogether. Wanted to see the internal execution of the views by seeing visualization plan. Now let us start today's session by seeing the visualization plan. So we'll log into HANA Studio. So I will take questions. So we have one question. I'll just answer this question quickly. How about calculation views of type cube? Okay, so calculate. I think I forgot this topic. Okay, calculation views of type cube. Now, what is the difference between using a calculation views of type cube and calculation views of type star join? The difference is in a star join, it is optimized to process for business suite on HANA. But you see, on the other hand, you have cubes. The calculation views of type cubes are used to combine data for, when you say cube executes on OLAP. A cube is a multi-dimensional view. So when you have two analytic views, now where is another object? Can we say, do we have any other object that where we can combine two analytic views? In calculation views, we have three data categories. One is dimension, cube with star join, and cube. Dimension is for master data. Cube with star join is for calculation views, wherein we cannot use analytic views. We also need an object to combine two analytic views. Nothing but calculation views of type cube. So a cube accepts attribute views, cube accepts analytic views. Because no other object accepts these both objects to do union, to do join, to do projection, aggregation, or ranking. So that's where we can use these cubes or attribute views, or even you can use calculation view with a cube. Any kind of information view we can use inside calculation views of type cube, because that is a limitation of the star join. So when you have a requirement to join or to union two analytic views, we simply go for calculation views of type cubes, which execute on C engine, So I log into the system. So HANA user. So first what we're going to see now, I'll log into HANA Studio. First we will see our data models. First we see our data models that we created. I'll expand system, expand content, and then let's go to let's take this view, AT customer. I'll right click on the view, and let's click on data preview. Click on data preview. Click on raw data. So when we click on raw data, I think there is some issue in the, you see when I right click on data preview, I see this 001 repeating multiple times. Let us see, is the data something like this, or there's no join on regio. So it is only showing on land 1, but countries and regions with this combination, otherwise it keeps repeating the same values. Let us right click on 80 customer, click data preview. I want to do a test. This is not relevant to this exercise, but just want to see. It's showing 36 entries. I think it's showing 36 entries. I'm just trying to see whether the data loading happened correct or not. Because we have data from multiple clients. So that is the reason you see it's showing the data was loaded from multiple clients here. So usually in the user, if you see in the user, we have something called I log to best schema. So this is the user for best. In here you have something called session client. Session client was not specified over here. So once the session client was not specified, so that's why it's showing data from multiple clients. So when we did a join on MA and DT, because the data was coming from multiple clients, then it's producing the right value. Okay, so today the topic was we were about to see when to go for visualization plan. I'll draw first like paint. So until now we understood that we have different views like attribute views, analytic views, calculation views of type cube, calculation views of type start join. So these are different data processing engines. So top these are views and these are data processing engines. Attribute views execute on a join engine. Analytic views execute on OLAP engine. Calculation views execute on C engine. Start joins execute on SQL engine. So here you have OLAP, C, SQL engine, calculation views of type cube, calculation views of type start join. Now what we wanted to see here is how do we confirm this is executed on join engine. Let us see this. How we know that this view is executing on join engine JE. So we'll go to the attribute view. We'll go to our package. We created these views on ECC March 7:30 AM package. Expand the package. Right click on customer, data preview, click raw data, and then let us click on show log. Double click on generate SQL. Copy the statement. Let us copy the entire statement. Let us open Notepad. Let us open a Notepad and copy paste the statement here. So here you see select top 200. Like this is columns, output columns, KUNNR. These are nothing but semantics. What we selected for output, land one based on the business requirement. So we require all these for output from where? From sysbic ECC March 7:30 AM. Now this is the column view. So I'll just show you the column view. First I'll go to sysbic schema. Let's go to HANA Studio and then expand the catalog. Let us expand the catalog. In here we find sysbic, expand sysbic, expand column views, right click on the column views and click filters and copy paste the column view. Click on whole word and click OK. Now, once we have this column view, double click on the column view. Here we see columns and create statement. So this is the statement that is generated by system. And this is the output based on my modeling. When I right click on this column view, I open data preview. I can see data preview right away here. So this is the data. So whatever I see in the attribute view, we can see this in the column view. Now, the same statement, when I right click on the system, click Open SQL Console, copy paste the statement, copy the statement and paste the statement, right click, format. So here you have the code that an attribute view selects to produce a result. We'll copy paste this code over here, right click on the code and click Visualize Plan and click Execute. So confirm perspective switch. Now it is trying to switch from HANA modeler perspective. It is switching from HANA modeler perspective to plan viz perspective. So when I click yes, and when I click executed plan, when I expand column search again, keep expanding this until you go to the bottom of the view. So here, we have now expanded this to until the bottom of the view. So this is the execution of the view. What you see here is the execution of the view. Now, when we click on this is nothing but timeline. When I minimize this timeline, here I'll click on the timeline over here. When I click on the timeline, and when we click on the timeline, we expand, and here you see at every step we see JE. We see JE, search on a table, JE. So the engine that is used inside an attribute view, whenever we execute an attribute view individually, it executes on JE engine. Now when it is search on a table, please see here, search on a table, basic predicate, SPRS is equal to E on T005T. And then here, based on the join, it is trying to, in the reduction phase, so here you have KNA1 T005T based on the data available in the table. So all this is happening in the join where KNA1 T005T and T005U, and finally the requested attributes from KNA1 table, KNR name1 land1, from T0 projection of the T005T, projection of T005U. It's trying to project from 3 different tables. So the output of 3 different projections, it is trying to assemble the result. Parallel execution of the query. It's trying to assemble from 3 different projections, each projection executed individually. And the 3 different projections executed individually. And finally, it does assembling of the result assembly. Once it does result assembly, finally the end user get the result. Why it is restricted to 200 rows is because by default, in attribute view, by default the maximum rows you can see here is 200. And this is the default indication. So based on the graphical view that we generated, system generates a column view. In the column view you have output and the statement. So based on the output and statement, this is the internal execution of the view, where the tables are individually executed, processed, finally assembled and give back the result. Now, let us go to each of these tables. Now when I expand, let us start from a table. Search on a table. Now when it does a search on a table, expand the catalog. Let us go to the schema called best, expand the schema. Let us go to the tables, expand the tables. Let us go to KNA1 table. KNA1 table. Double click on KNA1 table. Click on runtime information. Click on runtime information. And here the total memory consumption. The total memory consumption of the table is 3000. The number of entries inside the table is 19,000 records. Let me draw this table. So I'll draw this table. So this is the KNA1 table. Now we know KNA1 table is on memory. So how much memory it is consuming on the memory? 3409. It consumes 3409 KB of data in RAM. How many number of records we have? 19,575. KNA1 table has 19,575 records. Now all these records are stored in RAM. KNA1 table, we see there are few more properties inside the table. The KNA1 table, memory consumption in the main storage and the memory consumption in the delta storage. So a table is divided internally again into two parts. One is known as main store. A table is divided in two parts. One is known as main store and the other one is known as delta store. Delta. One is known main, the other one is known as delta. So KNA1 table is a customer master table. KNA1 table is a column store. The table is a column store. The table resides data in memory. These are the number of entries. The table has two parts. One is main and the other one is delta storage. The data in the main storage is the amount of data we store in the main storage is 1552 and 1857. So delta has 1857 amount KB of data. The main has 1552 KB of data. So when you basically plus both this, the total memory consumption is 3408 approximately. Now in HANA, tables are in memory, tables are column stores. A table is divided into main store and delta store. Now why a table is divided into two parts? Whenever we insert data into a delta, so we're talking about when it does a search on a table. Here you see there's something called search on a table. So when we talk about tables, these tables are accessed. It does search on both these areas. When you fire a query on the KNA1 table, for whatsoever reason, when you try to request data from KNA1 table, it searches on both these places, main and delta internally. Let's say I create a customer master record like 001. Customer name is Raju. He's from India and he's from Delhi. When I insert a record, when I insert a row inside a table, first this row comes to delta and the same row is moved to main. Now why is that? System first it has to take to delta and then move to main. Now please see, when I go and right click on a table, here we see something called, when I go right click on a table, here we see something called perform delta merge. What is delta merge? Delta merge is a process. Delta merge is the process of moving data from delta area to main area. Now, why it has to move data from delta area to main area? Delta area is optimized for writing of data and main is optimized to reads of data. Now why delta is optimized for writes and why main is optimized for reads? Whenever we move data from delta area to main area, data is basically compressed. It is compressed. So when the data is compressed, the amount of space that we occupy on the main is less when you compare with delta. For example, especially in HANA, we have, for say, 1 TB of data. 1 TB of data when you have on a traditional RDBMS like MS SQL. How much space does it require to store the same 1 TB of data in memory? It requires 250 GB. So 1 TB of data I can store in 250 GB of RAM. How it is possible? 1 TB on disk, which is on the MS SQL database. When I migrate this data to HANA, it only occupies 250 GB, means 1/4 of the space only it takes. Now simply to understand, 1 TB of data when you want to store on a disk, we want to purchase, it cost me around $50 to $75. But the same data I want to store it memory, the same 1 TB of data I want to store, it may be $3,000 to $4,000. So if I keep same data in memory, there is no greatness about HANA, because the money that you invest in the hardware will be so high, the customers cannot afford to buy HANA, because HANA is purely an in-memory database. So SAP thought, if the same data from disk is stored into the memory, RAM is expensive, and again we still store the same amount of data that was stored in MS SQL. We need to store the same data amount in memory. That's why what SAP has come up with something called compression. When you insert data into Delta, it's 1 TB. Data is not compressed, uncompressed data. But when you move the same data into main, the data is compressed. Means 1 TB of data in Delta, 1 TB of data in Delta, now it occupies only 250 GB in main. So once this data from Delta is moved to main, the data from Delta is deleted, and 1 TB of data is compressed to 250 GB. So how does this happen internally? Let us try to understand how this happens internally. Now, I'll take a simple example. In India, approximately there are more than 130 crore population, more than 130 crore population. For example, let us take Aadhaar card. Aadhaar card data we are storing in entire table, for example, means something like UID. For every citizen of India, we will have a unique identification number that will identify each citizen of India in a unique way. So that is nothing but UID, Aadhaar card ID. Now Aadhaar card ID is like 01 is citizen, 02 is a citizen, 03 is a citizen, 04 is a citizen. Now 1 is a male or a female. Let's say is male. 2 is a male. 3 female. 4 male. So in this way, every citizen of India, we need to indicate whether he is a male or a female. A male or female. Now in 130 crore population, so in every record we have to specify whether that particular record is a male or a female. So in 130 crore population, assuming that 70 crore population are males, and another 60 crore population are female. Now, male or a female is in a column called gender. There's a column called gender. In that gender column, we specify male or a female. Now, where is all this data stored? When you execute first time, it goes to Delta, because this is the entry point to a table. So now if I calculate how much a gender column, a column like gender, how much space does this column occupy on a table? I'll show you a small example. Now let us go to KNA1 table. If I double click on a table, if you go to columns, so how many columns do we have in KNA1 table? Let us see how many columns. We have around 194 columns. All the columns, when we sum up, this gives me the total consumption of the table. Each column has a space that occupies in memory. If I click on runtime information, if I click on columns, let us take one column like land 1. Land 1 is nothing but a column that gives us information about each customer belongs to what country. So land 1, how much space it occupies? It occupies around approximately 14 KB of data, 14 KB in memory. In 14 KB, the delta size is 10 and the main size is 4. Because the table is already compressed, the compression ratio for this table is 22%, and the number of records 19,575. How many distinct rows we have? How many countries does we have in this column? 41 entries like US, GE, Great Britain, India, Malaysia. So all these countries are in this distinct value. So unique values are 41. Okay. Now let us come back to the example. Now this column called gender, the column called gender basically has a space in memory. Now again this column space is divided in delta and main. Now the question here is how much space does it gender occupy in memory? Now when we say male, male is 4 alphabet. M is one string. Each string occupies approximately around 8 bits of data. 8 bits. 8 bits is nothing but 1 byte. So how many bytes do we require? So how many bits do we require? 8 into 4. 32 bits. 32 bits is nothing but 4 bytes. So 32 bits into, so how much population we have? 70 crore. 70 crore. This is what it stores in for male, and for female 6. So again the same calculation. So what I'm trying to say here is for every row we have to say whether it's a male or a female. So each row in a table, this male occupies around 32 bits, and 32 bits into 70 crore times it has to store the same value repeatedly. So is it not wasting our space on the memory when it stores repeatedly? So what SAP has done is, so let us not store the entry directly in a table. Let's store this entry outside a table where all the dictionary is stored. Like for example, if a table has male, internally it says male is equal to 1, female is equal to 2. So wherever it sees male, it's replaced with 1. Now what is the advantage of replacing a male with 1? Now 1 is an integer. If an integer occupies only 1 bit, so what are we trying to do? Male is a word that occupies 32 bits. So instead of storing 32 bits, we say mail is equal to 1 and 1 occupies 1 bit. So now I'm not storing strings. Instead of storing strings, I'm storing an integer. The string is stored in a different table called a lookup table, which is called a dictionary table. In here I will maintain the values, the distinct values. For each distinct value I'll say 1, the second distinct value is 2. So instead of storing mail, I replace with 1. Okay, the advantage. Now, what is the advantage here? Instead of 32 bits, I'm storing the same value in 1 bit. Compression. So when you move data from delta to main, delta merge. So delta merge is a process of moving data from delta to main. During this process of moving data, 1 TB of data becomes 250 GB because of this reason. Strings are converted to integers. Technically, the term used to convert strings to integers is known as encoding of data. We encode. So when you encode, you convert from strings to integers. Now, why do you convert strings to integers? Because it occupies less space on memory. Because memory is expensive. And we need to get return on investments faster. So SAP uses special algorithms which are known as run length encoding is one of the algorithm. Run length encoding, RLE. So SAP uses special algorithms to compress data. The data is compressed in main. A simple example would be if I upload 1 GB of data to my Google Drive is faster, or 1 GB I compress to 250 MB is faster. Obviously 250 MB is faster. You compress file, we use compress programs. We compress files and we upload data. So why do we compress data is because the upload can be faster. Now why main area is optimized for reads? Because the data is compressed. So when you fire a query, because the data is compressed, it can upload faster to the business. But we also understand when data is compressed, when business asks a question on the main area, it will start showing ones and twos. Instead of mail, it will start showing 1 because data is compressed and stored in main area. So instead of showing mail, it will show 1. So business cannot understand 1. What is 1 or what is 2? Business cannot understand. Again, what SAP has done is, when we store in a compressed way by using algorithms like run length encoding to store data to consume less space on memory. But when the business asks a question, we know when we ask a question, the request goes to the CPU. The request goes to the CPU, Central Processing Unit. Inside the CPU, you have different cache memories. Like inside a CPU, we know we have different cache, like L1 cache, L2 cache, L3 cache. So please see, I right click on my computer, I click on Task Manager, I click on Performance. So here we see CPU utilization. All these users are disconnected, but still see a disconnected user still running on the background. That's why it consumes a lot of CPU usage. Okay, so here what I'm trying to focus here is this is the CPU, nothing but this is the CPU, and this is the RAM. So how much RAM? 30 GB of RAM. When I click on resource monitor, when I click on resource monitor, so here you see this different CPU. CPU is running over here, the programs in CPU. So there's approximately 84 CPU usage. And the memory, this is memory, this is nothing but memory, this is the disk. This is network, disk, memory, CPU, overview. Overview of disk, overview of network, and overview of memory. So what I'm trying to show you here is the CPU. One minute. Let me open Google once. Let us try to open Google. Inside a CPU, let us go to any image. So here if you see, so in each core of a CPU, we have L1 cache, L2 cache, and L3 cache. L3 cache is a shared cache. L3 cache is a shared cache. So these are cache memory of a CPU. So if I go back again to Paint, so in each CPU you have different cache memories. Now most of the time the CPUs are so powerful, each CPU has different cores in it. You see here you have different cores, CPU 0, CPU 1, CPU 2. If you want to see cores, go to any device manager, I'll expand processors. So these are different cores in each CPU. So core 1, core 2, 3, 4, 5, 6, 7, 8. So we have, now this processor is a quad core CPU. The logical processors you have 8, but the processor is a 4 core CPU. So what I'm trying to say here is, these CPUs are basically available. CPUs are so fast, CPUs are so fast, whenever you fire a query on the CPU, L1 cache is the fastest cache, then L2 cache. The question travels this way: L1, L2, and then L3. From L3 it goes to the memory, from memory it goes to the disk. The slowest device is the disk, then you have memory, then you have CPU, again in CPU you have. Now, I was talking one question here. Whenever you ask a question, the system cannot show ones and twos again to the business. Decompression has to execute. So encoding is done. Encoding is a way to optimize to store data in memory, less space. But again, when you basically show data back to the user, it has to decode data. It has to decode. The decoding of data executes at the L3 cache memory of a CPU. So on the fly. Now why parallel processing of a query is required? When we store less data. When we want to see, it gives back the same data back to the business. So decoding executes in the L3 cache memory of the CPU, where it divides the query process, like you see the projection of KNA1, projection of T005T, projection of T005U. You have three projections. Each projection is being executed individually. And finally, on top of it, you have result assembly. You're assembling the result of these three projections executed individually. So each of these projections are executed in different cores of a CPU, where they decode data on the fly. Most of the time, if you see, CPU is doing nothing but being idle. Because it is very fast in processing when compared to memory, it quickly processes, it keeps idle. But memory takes time to process, and disk takes time to process. Disk is a very slow device, very time consuming, and then memory, then CPU, again in CPU, L3, L2, and L1. L1 is the fastest in any computer. L1 is the fastest cache memory. So the nature of the CPU is most of the time it is idle, doing nothing, because it is very fast. It quickly processes data, keeps idle. So what SAP has done is, most of the time CPU is doing nothing, being idle. So let us start utilizing the CPU power. So that's why they made these decoding algorithms to execute inside the L3 cache memory of the CPU, because CPU is doing nothing, being idle. They want to exploit the power of the CPU. At the same time, they want to make the HANA appliance cheaper, available to customer. Faster, at the same time cheaper. So when they store less data on memory by executing delta merge. Delta merge is a process of moving data from delta area to main area. Main area stores raw data, delta area stores compressed data. The compression is known as encoding of data. Encoding is nothing but converting from strings to integers. This conversion takes place in delta merge. Advantage, less space on memory. Less space on memory, faster upload to the business. But data is compressed. We have to decompress. Decompression executes in the L3 cache memory of a CPU. Because CPU most of the time is being idle, so SAP want to utilize the maximum capability of a CPU. So they execute inside a CPU, execute the query parallelly by executing the query in different cores of a CPU. That's why for HANA, you require a lot of cores. You require a lot of CPU power with ratio to memory. It executes inside the L3 cache memory of the CPU and gives back the result to the user. So two advantages. When we store less space. When we process the query, process the query, and give back the result to the user. So tomorrow we see theoretically on how this is functioning internally in a table. Tomorrow we see practically. Again, this delta merge is of three types. Delta merge is of three types. One is called hard merge, soft merge, smart merge. Hard, execute manually. When we execute manually, this is known as hard. System does automatically, auto merge, or also called as soft. Smart merge. Smart merge executes on the application layer of BW. On the BW application layer, smart merge executes. So tomorrow we'll see how practical. So just to conclude on this, memory is an expensive device. We cannot store the same data on the MS SQL and transfer the same data to memory. HANA primary storage is on memory. We need to find out a way to store data effectively in memory because it's expensive. So SAP found out a way where they divided one table into two parts, delta optimized for writes and main optimized for reads. Data from delta transferred to main via delta merge. Main compressed data by using different algorithms like run length encoding. They store data in a compressed way. The decoding takes place in L3 cache memory. At the same time, the speed at which the query is processed is maintained in the CPU because CPU, we are not utilizing CPU usage properly in the traditional software. So SAP, in using SQL script, they started to process the language parallelly. SQL, the parallel processing of query is done using SQL script. SQL script, the code itself, the way the code generates itself, internally it executes parallelly. Normally the programs have to be written in such a way they execute parallel, but the code is written by system for parallel execution by default. So store less on memory, effectively on memory, utilize the CPU capability so that the cost of the appliance is low. When the cost of the appliance is low, a lot of customers will start buying because it's cheaper and they can take business advantage in faster way and they can recover the money that they invested on the technology. So that is for today's session, and tomorrow we'll see the practically how this is internally executed in the system. Thank you. So here we have few questions. I will read out the questions here. So the questions are few questions are out of topic, but I'll just read out those questions. How can we compare the version of a view? I mean, how can we compare the active version in the production with the version of the development system? Just right click on the view and you have something called history. Click on history. When you click on history, it will give the versions of the view. And that way you can compare between production. See the right click on the production view and right click on the development view. Then you can see the version of a view. Next question. Can we please explain calculation views of type cube with example and also calculation views operators? So calculation views, as we see with example on the other day for COPA, and the different operators inside are you have join, projection, aggregation, union, and rank. Please explain rank. I will show you the rank functionality. Actually, in order to show rank functionality, I would like to show in the report. In report also you have ranking and backend also you can do ranking. So we'll compare both the rankings when we see web intelligence. When I integrate web intelligence with HANA, I will show you this ranking functionality. Why KNA1 is stored in column store? Why KNA1 is a column store? Master data tables are supposed to be in row stores. Is KNA1 not master data? Master data or transaction data, any data which is related to business, I mean business related data is always stored in column stores. Any data that belongs to not system data, not the system logs, the data that belongs to customer, my customers, my profit, my sales, All the data that is related to customers we store in column stores. Because we just understood the column stores are optimized for reads as well as for writes of data. For writing you have delta, for main you have reading of data. So when we start HANA Studio, we give a workspace in C drive. If we work on a different system, how should we import the workspace to that system? You can specify the drive where your workspace is stored. You're storing the workspace on the C drive. You can specify the path of the workspace on the local drive machine. So we have one more question here. I want to join two tables. One is a row store, the other one is a column store. Can we do that? Yes, you can do that. But best practice, avoid joining the row store with column store. Technically it is possible, but not the best practice. So what are the disadvantages? Because the disadvantage is nothing but you have to interact with two different engines. When two different engines come into play, two multiple layers, so you have two multi-layer. So when data has to transfer between two multiple engines to communicate to each other, we lose performance. So that's why even when you in a column store itself, when two engines come into play, like join engine and OLAP engine, SAP decided let us execute on a single engine on an OLAP rather than involving two engines. When we involve two engines have to communicate, we lose the performance. That's why always avoid taking consideration of two engines to be involved. So these are the questions. These are the questions we have in the chat box. Any other questions? Please type in the chat box. So can you please give a scenario for calculation use of type cubes? Yes. For example, let's say we have sales billing. You have a cube for sales billing and you have an analytic view for sales orders. Simple example I'll try to give. Or let us take the same example like analytic view for actual, analytic view for plan. We have two analytic views. Now these two analytic views are from BW powered by HANA. These are on BW powered by HANA. Now because we have two analytic views, now we want to combine these two analytic views and produce a result. So how can we combine? So we can combine using calculation views of type cube because we cannot combine them in a start join because start join doesn't accept analytic views. So because you want to combine, we have to create calculation views of type cubes. think we haven't seen, for example, on calculation views of type cubes. I'll show you in tomorrow's session. I'm just checking on the package here. I don't see this example here. So I'll discuss again in tomorrow's session, calculation views of type cubes, once we complete this topic. Let me complete this topic. The column stores the practical. Once we complete, I'll revisit again to calculation views of type cube. Well, thank you everyone to attend today's session. Hope everyone had a nice weekend. I'll see you tomorrow same time. Have a great day. Good morning and good night to everyone. Thank you.